folks, this is Thomas from thermodynamics class, and today I'm going to present you a problem that is solved with the Thermosolver. And this problem is based in basically two things. The first one is that we are going to have a system with pure air at 40 bar and 25 centigrade from temperature. And we want to know which is the fugacity and the fugacity coefficient. As we have seen in other courses, we have many ways to calculate this thing, but today we are going to use the Thermosolver to do it. So there you go, you open the Thermosolver. Could you put correctly the slide? Yeah. There you go. This is the Thermosolver. And here we have many options. The first one, it's a space state base, saturation pressure calculator, equal state solved, board. The one that we are going to use today is the fugacity coefficient solver. So we put it, and if you want to record like more, it's great. Okay. First of all, here they put add one or more species to the system to enter a temperature and pressure. The fugacity coefficients are listed in the summary table. The model values are in the summary table, may be edited. Okay, so as we saw, the air is basically composed by this. We have nitrogen, oxygen, and argon mainly. So we are going to put like this in our Thermosolver. And the Thermosolver asks us for how many moles do we have of each thing. So we're going to have a base like 10, our base will be 100 of mole. Okay, so for the nitrogen we're gonna have 78 moles. After that 21 moles of oxygen, and at the end 7 points. I'm sorry, this is not true. Just 0.07 moles of argon. So we're going to put this in our Thermosolver. We're going to add a species of the system. First we have argon, so we're going to put the number of moles, 0.7, add to the system, and right now I have it. After that I'm gonna add the nitrogen. Let me search for it. The nitrogen, we have many species here. Well, I find the oxygen. And the oxygen, we have 78 moles. I'm gonna add it to the system. And, wait. And after that, we're gonna add the nitrogen, right? Here at the pure thing, we have 78, right? So I have, just wait, I have an error here. I put the oxygen that it's 78, but that's not true. It's 21 moles. So let me search for it again. Here you go, oxygen, and it's 21. Now, I have add all our species in our system, but I need to put now the conditions that we have in our system, that is the temperature and the pressure. So I'm going to change here to centigrades to put 25. After that, I'm going to put the 40 bars of pressure. And now this is very important because we have two different ways to obtain the fugacity coefficient. It's the Pin-Robinson equation on the Lee-Kissler. We're going to put the Lee-Kissler equation, right? So as you can see, we have here all our fugacities, but they are mainly just from each component. So how are we going to put the total fugacity? That is our problem. Let's see it this way. The total fugacity, because we have a mixture, right? Mixture. Now, we want the fugacity of the mixture, right? Fugacity. So we have our composition, and we are going to multiplicate our values of coefficient of independent species multiplied by its amount in our whole system. We are going to make that calculation and we are going to obtain the fugacity. So we have 0.78 fraction of mole plus, no, multiplied by its coefficient. This one is the nitrogen. As we could see, the nitrogen is the number 2, and we have 0.9932. Okay, we're going to add now the oxygen. In the oxygen, we have the 0.21% of everything multiplied by the coefficient that we obtain in the Thermosolver, and at the end the argon, that it's not just the only species that it's also present on air, but it's the one that applies like after these two other compounds. So we're going to add this 0.0007 multiplied by 9765. This will give us the fugacity. And which is the result of, have you do it? Or
Yes. Potential por la presión.
this plus the pressure, right? We have here 7.81514. Now, this is the total coefficient, right? This is the total coefficient. We're gonna add this symbol because it means that it's from all the species that we have. Now, we want the fugacity. As we know, the coefficient of fugacity is equal to the fugacity divided by a pressure that we determine. And this pressure will be our pressure of the system, initial system. So we're gonna put like this here, and I'm sorry for this. This is equal to the coefficient only, okay? So the fugacity will be equal to our last amount, well, our whole amount of coefficients here, plus our pressure that we determine at the system. This is equal to the number, it's 7.81514 plus multiplied by our 14 bars. I'm sorry, because running out of space. I'm gonna put it here. Our total fugacity will be, wait a second, please. It's 7.81574 multiplied by 40 equal. This is 2.73 bars. And how could we justify this solution? Because as we could see, our air, it has the comportment of an ideal gas, because it doesn't have a lot of energy, it doesn't make a lot of destruction in the system. So that's why we have this fugacity, and that's why we could see in our Thermosolver that all the coefficients of fugacity of each amount, it's very high, because we know that for ideality the fugacity is 1. So thank you very much. I hope that you learn and enjoy this session, and wait for more to next week. Thank you.